Good morning, everyone.
Good morning, sir.
Sir,
Okay, today is the lecture number 3 of this advanced concept in steel technology, and today we're going to discuss about these microstructures, which are very important because, as you people know, microstructures always affects the properties, right? And since we people are belongs to metallurgy and metallurgical engineering people, so we know the techniques so that we can change the microstructures, right? And we know that if we able to change the microstructure of basically steels, we can able to change the properties, and depending upon our requirement we can modify the structures. And if you remember, what are different microstructures in steels? If microstructures means basically, if you put the sample under a microscope, what are the things which will be visible, right? Those are microstructures like grains, grain boundaries, your porosity, if any, and if any different phases will be present. All those are, and dislocations. If we look the sample under transmission electron microscope, right, we can able to see dislocations, defects. Those are defects, right? So these are basically microstructures, and some precipitates you can able to see if it have, right, some carbides, some nitrites, those things, right? So these all are microstructures, or we can say nanostructures also, because some of the precipitates, those are of nano size range. So these, if you change them, you can able to change the properties, right? So that is also called structure property correlation, right? For example, suppose I'm talking about grains, let it be grains, because under a microscope you can able to see some grains, right? If you have lot of grains, you can able to see, if you can see a lot of grains, that means a lot of grain boundaries are there, right? So a lot of grain boundaries means a lot of obstacles before the dislocations. So a lot of obstacles before dislocation means dislocation cannot move easily in that material because of hindrance provided by the grain boundaries, right? So that means that is a fine microstructure, a grain with fine size or very small size grain. So that will provide you high strength and high toughness, right? Similar, just opposite, if you can able to see a small big size grains under a microscope, that means less number of grains are there, so obstacles will be also less. So that means that kind of material will give you more ductility, more toughness. The strength will be less. This is one of the example I'm giving. Another example, suppose you are looking at the microstructure, or you can able to see a lot of dislocation density is present, right? By using transmission electron microscope we can able to see dislocations, and if you can see a lot of dislocation is there, that means the dislocation density is very high. That means it, that material will have high hardness and high strength again. Similarly, suppose you can able to see some porosity inside the material, that means the material will have less strength, because you understand the pores are the crack initiation points, because of high stress concentration over there. Similarly, suppose you have two steels of same composition. In one steel you are seeing some ferrite and some perlite is there, but in another same steel you can able to see martensite is there, right? So what is the difference? The steel which is showing martensite, that means it is a very hard steel, that is stronger steel, it is having high strength, right? But the steel which is showing ferrite and perlite, it is softer somewhat, it is ductile and tougher, right? So I think you people are getting my points. So how microstructures affects the properties, and that is, so that means the motivation to this topic is you should have a good knowledge about the different phases or different microstructures present in steel, so that you can able to justify the different properties or how they will behave. That means they will behave as a ductile, or they will behave as a tougher material, or they will behave as a high strength material, or like that. So okay, I'll move to the contents. You can see this is a microstructure and this is a microstructure. So in these two microstructures, what we can able to see here, we can able to see grain and grain boundaries. Here also we can able to see grain and grain boundaries. But what is the difference? The difference is, in this case we have larger size grains. The grains are bigger, but here the grains are smaller comparatively, right? So this is a microstructure of ferrite and this is a microstructure of austenite, right? Because you understand, if we are only seeing grain and grain boundaries only in a microstructure, that means it is a single phase. So ferrite is a single phase and austenite is also a single phase. The difference is that the austenite is bigger grain size, the ferrite is smaller grain size. That is the difference. Okay, this image. So these are various microstructures which are obtained during different cooling rate. Suppose your starting microstructure is austenite. You understand where austenite forms. It forms at a high temperature, basically. So from austenitizing region, if you're cooling your steel at a different cooling rate, so what are the microstructure you will get? So yes,
Hello.
yes, Mansi.
Hello.
Yes, Mansi, you are audible. You can speak.
Sir, can you please enlarge the slide?
Okay, let me enlarge it.
Can you please enlarge the slide? Can you please enlarge the slide?
It is okay right now? This is okay?
Yes, sir.
Okay, fine. So we can have different microstructure on due to different cooling rate. That means very slow cooling rate, medium cooling rate, and high cooling rate, like that. Yes, yes, Mansi. Okay, so this is a microstructure of ferrite. This is a microstructure of perlite. This is a microstructure of bainite, and this is a microstructure of your martensite, right? So this is the order of cooling rate. If you are increasing the rate of cooling, you will end up with martensite. If the cooling rate is moderate one, then it will end up with bainite. If the cooling rate is very slow, you will end up with perlitic microstructure. And ferrite, it depends upon the type of steel, because the combination, you can get a combination of ferrite and perlite. Or if it is an eutectoid steel, you'll get only 100% perlitic microstructure, right? And you remember, if Bainite is a microstructure which is obtained due to isothermal cooling, right? Not continuous cooling. But this is very interesting. You have to first quench the steel from the austenitizing temperature to the Bainitic range temperature. First, you have to do quenching, very fast rate of cooling, and you have to stop the cooling at Bainitic temperature region, and you have to allow the steel to cool isothermally, that at constant temperature it has to cool. So you'll get Bainitic microstructure, right? And this is the order of strength also. If you measure the strength of the material, that means you have a same steel, the composition of steel is fixed, right? But you are getting different microstructures. Suppose you make 4 cross sections out of that. In one cross section we are getting this, in one cross section we are getting this, we are getting this, and we are getting this. That means this is the order of increasing in the strength, order of increasing in the hardness value, right? But the maximum toughness will get here, in this case Bainitic microstructure. Maximum toughness. But this is the order of increasing in the strength, and this is the order of increasing in the hardness value. The soft one is the ferritic one. This is a very soft and ductile one. But toughness is very poor here. Toughness is good here, good here. And sometimes here also, it depends upon the type of martensite, because we can have a martensite and we can have a tempered martensite. I will show you later. Okay, now this is the question. Just okay, sorry. Look at this one. Plain carbon steel microstructure with carbon of eutectoid composition, less than eutectoid composition, and more than eutectoid composition. So now my question is, can you people arrange them according to their composition? So So which microstructure is of Euctectoid composition, which one is of less than Euctectoid composition, and which one is of more than Euctectoid composition? Tell me quickly. In the previous lecture, I have shown you the evolution of microstructures of different steels: Euctectoid steel, hypoeutectoid steel, and hypereutectoid steel. Less than Euctectoid composition means hypoeutectoid steel composition. More than Euctectoid composition means hypereutectoid steel composition. So you have to arrange them according to Euctectoid composition, less than Euctectoid composition, and more than Euctectoid. So tell me quickly, first, which one is the Euctectoid composition? Which microstructure will show you the composition of a Euctectoid steel? First, second, or third? Do you want me to show you that slide where I have explained you about the evolution of microstructure?
Yes, sir.
Okay. This one. This one is Euctectoid microstructure. This one is the hypoeutectoid microstructure, and this one is the hypereutectoid microstructure. These are cartoon diagrams, but those are real diagrams. Okay, this is one part. And this one. This is your hypereutectoid composition. Less than this one. Less than Euctectoid composition. This one is your Euctectoid composition microstructure. And this one is hypoeutectoid composition, less than Euctectoid composition. Okay, now tell me quickly. So in between these three microstructures, which one is of Euctectoid composition, which one is of hypoeutectoid composition, which one is of hypereutectoid composition?
First one is eutectoid,
Very good.
second hypoeutectoid, a third
Very
one
good.
hypereutectoid.
Very good, very good, very good. The thing is, what you can see here, only perlite is there. 100% perlite is there, right? Perlitic colonies are there, right? One colony. This is one colony of perlite. This is another 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 colony of perlite, right? So 100% perlite is there, right? So 100% perlite forms at the Euctectoid composition, that is 0.8 weight percentage of carbon in steel, right? So this is an Euctectoid composition microstructure. But here, how perlite, you can understand. Here it is showing alternate layer of ferrite and cementite. The white portion is suppose ferrite and darker portion is cementite. Ferrite, cementite, ferrite, cementite, ferrite, cementite, like that. But you can able to see here, these darker portions are what? Which phase? The entire darker portion is perlite. What? How cementite? Just look at this image carefully. You can able to see some darker and lighter, darker and lighter, darker and lighter portions. So this is a perlite, not cementite. This one. Suppose I'm looking showing you this one. This image. Again, suppose this is one. So these are perlites. The darker portions are perlites, right? And these lighter portions, these are lighter portions. They are lighter. These are ferrites. These are basically pro-eutectoid ferrite. These are pro-eutectoid, lighter pro-eutectoid ferrite, and these are perlites, right? So this is obviously less than eutectoid composition microstructure or hypoeutectoid steel composition microstructure. And this one, Mansi, can you tell me what is the difference here? As you told, this one is of hypereutectoid. How you can justify that?
Sir, because white portion is the network of cementite.
Very good, very good. Because you can able to see along the grain
Because
boundaries.
in that diagram, the grain boundary region.
Yes, grain boundary region. So here the grain boundary is having a network structure. You can see this is a complete network.
It is present along the grain boundary.
Yes. So that means cementite has formed and it has grown along the grain boundaries. So a network of cementite has formed, right? And this inside the grain is perlitic structure, because alternate layer of ferrite and cementite is present. Darker, lighter, right? So obviously, so this is a hypereutectoid composition steel microstructure, fine. So if you check the strength and hardness, it will be here high, right? Basically, but it is a brittle kind of structure because due to network of cementite, harder and brittle. And this is having good toughness, and this is having basically this is having high strength and high toughness, and this is having some ductility because of ferrites, more ferrite. Now I'll show you some ferrites. We can have one type of ferrite called allotriomorphic ferrite and idiomorphic ferrite. What is the difference? Can you people tell me by looking at this microstructure? This is a cartoon microstructure, and also real microstructure looks like completely like this only. Three things I have shown here. One is this is what? This entire is a grain, right? This is a grain, and this is a grain boundary, right? But this is actually called, can you people tell me what is the name of this grain boundary? I told you earlier. What is the name of this grain boundary? This is an austenite grain boundary, but what is the exact name of this grain boundary? What is the exact name of this grain boundary? Prior austenite grain boundary. Do you remember that right now? Can you recall prior austenite grain boundary? Why it is called prior austenite grain boundaries? Because earlier the initial phase is austenite, right? Only grain of austenite is present. That grain boundaries are austenite grain boundaries. But that has undergone transformation. Austenite has undergone transformation into some different new phases. Here the ferrite is a new phase coming out. And you can see one kind of ferrite is forming along the grain boundaries. So it is taking the shape of the grain boundary. So that is name is allotriomorphic ferrite. Allotriomorphic ferrite means the ferrite which has formed along the grain boundaries and it has grown along the grain boundaries finally. And it is not having irregular shape, not regular shape. But you can see a ferrite which is nucleated inside the grain boundaries. Sorry, inside the grain. So this kind of nucleation happens if some non-metallic substance will be present. If there is some non-metallic substance, non-metallic inclusions, this leads to formation of this kind of idiomorphic ferrites, which are having a particular crystallographic shape. A proper shape is there. That is the difference between them. Now look at this microstructure. This is again a cartoon microstructure. This is not an original microstructure again. But you can see these are three grains of austenite and grain boundaries is here. But this is a plate-like structure. This is actually a plate of martensite. And this is another plate of martensite. This is another plate of martensite. So basically in 3-dimension, the martensite, the ferrite, Widmanstätten ferrite actually, martensite, Widmanstätten ferrite and Bainites are plate-like structure in 3-dimension. But if you look into the literatures, textbook, they have written some needle shape, some fidri shape, but that is also fine. But if you look at the real microstructure in 3-dimension, those are basically plate-like structure, plates. And can you people tell me this is which kind of ferrite now? Just before I have explained which kind of ferrite is this now. Allotriomorphic ferrite. Why? Because they have nucleated along the grain boundaries and growing along the grain boundaries, right? So this is an austenite grain. This is a prior austenite grain boundaries now, and this is an allotriomorphic ferrite, and this is a martensite. You can able to see martensite do not grow beyond the grain boundaries. It starts from the grain boundaries and end at the grain boundaries, right? Okay. So now I'll show you cartoon diagrams of upper and lower Bainite. So Bainites are two types, upper and lower. Upper Bainite means that Bainite forms at a relatively high temperature resistance. For example, it is in the range of 550 degrees centigrade to, for example, 350 degrees centigrade, like that. But if the bainite will form at a relatively lower temperature, like at 250 degree temperature or at 300 degree centigrade temperature, right? So that is your lower bainite. So this is your cartoon image. You can able to see this is, as I told, in 3 dimension, bainite is a plate-like structure. So we can have a plate of ferrite. This is a plate of ferrite. This is a plate of ferrite, and this is a plate of ferrite. Here also we have plate of ferrite, plate of ferrite, and plate of ferrite. But these darker regions are cementites. Because I told you what is a bainite. Bainite is not a phase. Bainite is a mixture of phase. Why? Because it is a mixture of ferrite and cementite particles, right? So it is a mixture of phase. Again, perlite, if somebody will ask what is a perlite, do not say perlite is a phase. Perlite is a mixture of phase because it is a combination of what? Ferrite and cementite, right? So now you can see what is the difference between upper bainite and lower bainite. You can see the distribution of cementite will decide whether it is a upper bainite or whether it is a lower bainite. You can able to see it is a sandwich-like structure, right? Because the cementite particles has precipitate in between the plate of ferrites. In between the plate of ferrites, the cementite particles has precipitated. Cementite particles are absent inside the ferritic plates. But whereas the distribution of ferrite is in between the plate here and inside the plate, you can see these are the ferrite cementites, which has nucleated inside the plate of ferrite, and some cementite are in between the ferritic plates. This is the difference. And another difference is lower bainites have high toughness and high strength as compared to upper bainites. And lower bainite is more finer in microstructure. If you look at the microstructure, these are more finer. These are somewhat coarser compared to that. And the interesting point I would like to mention here is you can able to see the length of this ferrite plate, 10 micrometer, and width is 0.2 micrometer. If you look at the wavelength of the normal light, the ordinary light, it is greater than 0.3 micrometer, or it is nearly 0.4 micrometer, greater than 0.3 to 0.4 micrometer. But the dimension of this ferrite plate is 0.2 micrometer. That means the wavelength of ordinary light is greater than this dimension. So that means this plate cannot be resolved with the help of ordinary microscope. That means optical microscope, because in optical microscope we use ordinary light. But if we are using electrons microscope, because the electron wavelength is very low, so we can able to resolve them. We can able to see these features easily. But these features cannot be resolved using ordinary microscope. You understand the reason I told you. Next, this is a real microstructure or micrograph of a bainite by using transmission electron microscope, right? So can you people tell me, by looking at this image, this is the upper bainite or lower bainite? And you have to justify that. I will take you 5 seconds to think of this. Take 5 seconds and tell me if this is an upper bainitic microstructure or lower bainitic microstructure. I have shown you this one. Just compare this figure with this one and tell me.
The lower bainite.
This is a lower bainite. Okay. Anybody else? How many of you are saying upper bainite? Just take this one at least. This part. At least take this part. You can easily understand then. This part is clearly visible. Or this part is clearly visible. This is an upper bainite. Just look at the upper bainite. This is a plate of ferrite, plate of ferrite, plate of ferrite, and cementite is in between them, right? But in this case, some cementite has precipitated inside the plate, right? So just look at here. This is a plate of ferrite. This is another plate of ferrite. This is another plate of ferrite, right? So in between this plate and this plate, cementite particles are precipitated here. This in between this ferrite and this ferrite, a cementite particle is precipitated here, right? So this is an upper bainite, not lower. Suppose this is a plate of ferrite, and this is a plate of ferrite. This is a plate of ferrite, and this is a plate of ferrite. Now, so in between them, cemented particle has precipitated. So this is an upper bainite, right? Okay. Anyways, and another interesting point I would like to tell you that if you really resolve these portions, these portions, this is a subunit growth mechanism. It is looking like that. This is a whole bainite, but actually this is not a whole bainite. This is a whole bainite. This is looking like this is a whole bainite, right? But this is not a whole bainite. This is a subunit growth mechanism. Subunit growth mechanism means what exactly happening? A small plate of bainite will grow and it will stop. Again, a new bainite will nucleate and it will grow and again stop. Again, a new, where it stop, again a new bainite will grow and it will stop. Again, a new bainite will grow and it will stop. This is called subunit growth. Subunit means a small unit of bainite will be there. It is not like this is a whole bainite. You understood? This occurs, let me justify this, why this occurs. Because you understand, when bainitic transformation will happen from austenite, that means austenite is a very soft phase, it is a ductile phase, and a bainite is growing. When a bainite grows, it deforms the austenite. A large shear will be there. Due to a large shear, the parent austenite will get deformed. Can you people tell me, if it will deform, what will happen to the boundary between the austenite and bainite? If austenite will get deformed, what will happen? What things will form at the junction or the boundary between the parent austenite and bainite? What kind of things will form? When a material deform, what things form? What kind of defects form when material will deform plastically? What kind of defects form when a material deform plastically? Have you attended the previous lectures of mine? Large amount of strain will generate, but why they will generate? What is the reason? What kind of defects generates when you deform a material? Dislocations. So obviously dislocations will generate, right? So you understand, if bainite is nucleating and growing, but due to its growth, it will deform the adjacent austenite. So what will happen? A lot of dislocation will generate. So that will lead to strain hardening, right? When a lot of dislocation will be there, it leads to strain hardening effect. So once strain hardening effect will come out, what will happen? The strength of the austenite will increase. So what happens? The bainite cannot grow further. There will be no more bainite formation. It will stop over there. So that means, this is very interesting. The bainite, upon growing, kill itself. The bainite killed itself during its growth due to this plastic deformation in the austenitic phase. A lot of dislocation will generate that will lead to strain hardening. So what happens? A new bainite will nucleate and start growing. Again, it will get killed up by itself. Again, a new bainite will nucleate and grow and it will kill itself. So that is called subunit growth mechanism. I think this part is clear. Next, we'll move to equilibrium phases and mixture of phases details in iron carbon phase diagram. If you have an iron carbon phase diagram, these are all equilibrium phases. Austenite, alpha ferrite, 100% perlite, cementite, ladybirite. These are all different phases and you already have a good idea about them. I'll just talk about some features, their mechanical properties and magnetic properties. Alpha ferrite or ferrite, simply called ferrite or alpha ferrite. It is, we know that is a BCC structure, body center cubic structure, and basically these are ferromagnetic, but up to 768 degrees centigrade. That means low temperature ferrite is magnetic, ferromagnetic, strongly attracted by magnet. But once if you go above 768, it will become paramagnetic, right? And ferrite is a very soft and ductile phase. And maximum solubility of carbon is 0.025. In some literature, you can see 0.35 like that. 0.0, sorry, I'll edit that. So 0.025 is the maximum solubility. Okay, let me edit it. 0.025 is better to write. Then austenite. Austenite is a high temperature phase, right? It is again a single phase. It is FCC structure, but this is non-magnetic. You have to remember, austenitic steels are non-magnetic. So if steel having only austenite, it is non-magnetic, right? But it is soft and ductile. Why soft and ductile? Because it is a high temperature phase. At high temperature, becomes the yield strength decreases always at high temperature. The yield strength always decreases with increasing in the temperature. You have to remember that. So austenite is a soft and ductile phase. And maximum solubility is 2.1. Maximum solubility of carbon. Delta ferrite is again high temperature phase, just below the liquidus temperature. It is again BCC, but the mechanical properties is set. We can call it is also ductile somewhat at high temperature. At high temperature, but at room temperature, it may have some other properties. But basically, at high temperature, it is ductile. Then 100% perlite. 100% perlite is tougher, harder, and good strength, but it is magnetic, right? And as I told you, it's a mixture of phases, ferrite and cementite. Cementite is the crystal structure is complex orthorhombic, and is ferromagnetic below 210 degrees centigrade. But above 210, it is paramagnetic again. But it is a very hard and brittle phase, poor toughness, but a high compression strength is there. Maybe in later class, I will tell you how it is a high compression strength. But it is an intermetallic phase basically. The carbon weight percentage is 6.67. In ledumbrite is a eutectic mixture of austenite and cementite. And what about this property? I have no idea. And the average composition is 4.38% of carbon. And different transition temperatures. Different transition temperatures may be also called as critical temperatures. Critical temperature is the temperature at which phase transformation initiates or starts. A phase transformation happen. Phase transformation means the change in crystal structure will happen. The initial crystal structure will change into another crystal structure, right? A magnetic transition temperature means the magnetic property will change. That means ferromagnetic property may become paramagnetic with increasing in the temperature. Similarly, with decreasing in the temperature, the paramagnetic nature will convert into ferromagnetic nature. That is called magnetic transition temperature. So this transition temperature happens at a particular temperature, right? Sometimes the critical temperatures are variable also. It is not fixed. I'll show you sometimes. So the name are like this: A0, A1, A2, A3, ACM, and A4. Some people write AE1, AE3, E represent equilibrium. But the thing is same. AE1, AE3, AECM, right? E represent equilibrium, right? AE4. So from this all temperatures, critical temperature is what? This is the critical temperature. AE1 or A1 is the critical temperature. And A3 is a critical temperature, or AE3 is a critical temperature. This ACM is also a critical temperature. A4 is also a critical temperature. That means this one, this one, this one, this one. Here, the phase transformation will happen at this temperature. If you're rising the temperature or if you're going down the temperature, right? But A0 temperature and A2 temperature are magnetic transition temperature. Here, magnetic property will change. Para to ferro or ferro to para, depending upon you, whether you are rising the temperature or whether you are decreasing the temperature, right? Okay, and A1 temperature, A1 is called lower critical temperature, and A3 temperature and ACM temperature are upper critical temperatures. These are upper critical, this is upper critical. This is lower critical temperature. And AE1 temperature is also called sometimes eutectoid temperature. You have to remember. A1 temperature is also called eutectoid temperature. And I have written over here, you already know these things. Now I'll show you the very good plot. This is the temperature axis, and this will shows you whether the nucleation rate will be high or growth rate will be high. So this is a temperature axis, and I have divided the temperature into two halves. This is the division. So above this, the temperature is high, and below this temperature is low. So this, if you're moving down this temperature from high temperature to low temperature, what happens to the nucleation rate and what happens to the growth rate? Nucleation rate, you people understand, if the nucleation rate will be higher, that means more number of nuclei will form. Do you people want me to write something here? Do people want me to write? I think okay, here it is written anyways. Okay, I'm writing here. High nucleation rate. High nucleation rate means what? More number of nuclei. More number of nuclei means small grain size. Right? This is one part. High growth rate means less number of nuclei. Less number of nuclei. Less number of nuclei means what? Bigger grain. Bigger grain means, okay, bigger grains. If you look into the properties means high strength, hardness, high strength and toughness, a good toughness. Right here it is high ductility. High ductility, right?
No, sir.
Yes.
So low ductility, na?
Which one?
Bigger grain.
Bigger grain, low ductility? What you are saying?
Means, sir, means
What
that
you are
will
saying?
be,
Okay. You tell me, yeah. What you are saying, yes.
sir, means small grains means they have a finer grain structure, and bigger
Small
grain
grains is finer grain structure. Very good then.
means bigger grain means core structure.
Core structure, very good. Then
Core structure have less ductility.
core structure have less ductility. Who told you this one? Just tell me
Okay.
from which literature you have studied or from where you have got these things.
Not exactly knowing, but
No, how you can you justify that? How? I need the justification. What about other people? Do you are you agree with this, Vijay? Do you people agree with this Vijay statement?
sir, actually, if there
Yes.
is means if there are more grain boundaries, then the growth is less. So means
You are listening my lecture. What I have told about the fine grain structure, why the strength of fine grain structure is more. Are you listening my lecture? What I told. If the grain size will be smaller one, that means more number of grain boundaries will be there. And if more number of grain boundaries will be there, more number of obstacles will be there, more number of hindrance will be there for the dislocation motion, because dislocation cannot cross the grain boundaries. Dislocation is moving, but it is coming in, but it is interacting with the grain boundaries. So it is getting piled up. Do you know that? Those things. So if more number of grains will be there, that means the grain size is less. So it is small grain. Small grains means more number of grain boundaries. More number of grain boundaries means more number of obstacles. More number of
yes, sir.
obstacles means more is the strength, because dislocation cannot move. Now you got the point again?
Yes, sir.
Yeah, the
Yes,
same
sir.
thing I have told you.
Yes,
Yeah.
sir. That I agree. But for bigger
So
grain,
that means you have no idea the relationship between ductility and strength. Are they directly proportional or inversely proportional?
ductility and strength.
Yes.
So directly proportional.
Directly proportional, what you are saying? Oh my God. Ductility and strength are directly proportional, you are saying? Impossible statement. If a strength of a material is increasing, means its ductility is decreasing. If ductility is increasing, means the strength is decreasing. If a material is deforming to a large extent by plastic deformation, that means it has good ductility and poor strength. But if a material is not getting deformed to a large extent, that means it has high strength, low ductility. You understood now?
Yes, sir.
It is okay to everybody? Shall I move on? Okay, I think you people understood. High nucleation rate means more number of nuclei will form, and small grain size. It will end up with small grain size or fine grain, right? So the properties will be high strength, high toughness. But if the growth rate will be high growth rate, then less number of nuclei will form. It will grow into bigger grains, coarser grains, and high ductility and low strength will be there. Or in other words, I can write rate is inverse to growth rate, right? If the growth rate is high, nucleation rate will be less. If the nucleation rate will be high, growth rate will be less, right? Anyways, so what I mean to say here, you can see this is a temperature axis. This is the division between the temperature. This is the high temperature. This is the low temperature. So now you can see the plot. Can you people figure it out what is happening? The relationship between the temperature with the growth and nucleation rate? By just looking at this figure, can you people tell me what this figure is showing? What is the relationship between temperature and growth rate and temperature and nucleation rate?
It's higher at low temperature and lower at higher temperature.
If this figure is showing, you can see the growth rate is increasing, right? And again, it is decreasing here. But the nucleation rate is increasing in this trend. And again, it is decreasing in this trend, right? So you understand the growth rate is higher. You can see the division of temperature. The temperature has been divided into two parts. This is the low temperature and this one is the high temperature. So growth rate is high at high temperature, but nucleation rate is high at low temperature. Now you got the point? It is okay?
Yes, yes, sir.
So growth rate is higher at high temperature, but nucleation rate is higher at low temperature, right? But what about this temperature? I will take the intermediate temperature, not so high, not so less. This is the optimum temperature, right? There will be optimum growth and optimum nucleation rate. Both will be good. So at this temperature, the nucleation rate will be also good and growth rate will be also good. There is an optimum growth of nucleation rate and growth rate, right? And I told growth rate is inversely proportional to nucleation rate is inversely proportional to growth rate. I have shown you here. So now, can you people, okay, let me justify this. Growth rate is higher at the high temperature because at high temperature, the diffusion is higher. The diffusion is higher. Since the rate of diffusion is more and more, growth rate is more. But in case of nucleation rate is higher at low temperature because the thing is what? With going down the temperature, we are doing undercooling. So more is the undercooling, more is the driving force for the nucleation to happen. So if there will be more driving force available for the nucleation to happen, more number of nuclei will form. Right? So this is the answer. I think you people understood. Why nucleation rate is higher at low temperature? Again, I'm saying nucleation rate is higher at low temperature because more is the lower. If you go down the temperature axis, you are doing more undercooling. If you're doing more undercooling, that means the driving force for the nucleation will be more. More is the driving force for the nucleation, more is the number of nuclei. Now this is TTT diagram and CCT diagram. You people understood. This is the TTT diagram and this is CCT diagram. So you can see in the TTT diagram, we have a temperature axis in degrees centigrade, and in the time axis, this is the actually log T. It is only T, but time it is written in second, but it is log T. You have to remember temperature versus log T, because we have to show you very small temperature and high temperature here. That's why we've taken log scale. And you can see this dotted line, dot line. So this dot line is what exactly? Can you people remember? What is this dot line showing?
Sir, above that there is liquid. Liquid phase is there above it.
Liquid? What you were saying? TTT diagram is never drawn for any liquid to solid transformation. It is only drawn for solid to solid transformation. Basically, you can draw a TTT diagram. That is fine. You can draw a TTT diagram for liquid to solid transformation. But the point is here written, eutectoid temperature. Just read it.
Okay.
This dot line is a eutectoid temperature. This is actually AE1 for which steel? AE1 for which kind of steel? Hypo or hyper or eutectoid?
Eutectoid steel.
Eutectoid steel, obviously, right? This is actually, otherwise you can write eutectoid temperature or you can write AE1. AE1 means E for equilibrium. AE1 is a equilibrium transition temperature, right? Critical temperature. This is a critical temperature. Critical temperature means at this temperature phase transformation will start. If you're going down the temperature, even if you're going increasing the temperature, again the phase transformation will start, right? So above this temperature, you have which kind of phase? Austenite, right? And below this temperature, austenite become unstable. So once the austenite become unstable below this temperature, it will undergo phase transformation. It will transform into either coarse perlite, it can transform into fine perlite, it can transform into upper bainite, it can transform into lower bainite, or it can transform into martensite, right? So you can see gamma means austenite is transforming into perlite, gamma is transforming into bainite, gamma austenite is transforming into martensite, right? So below this temperature, austenite become unstable, and due to unstable behavior, it will transform into some new stable phase, that is perlite or bainite or martensite. But basically, you have to remember, martensite is a metastable phase, not a stable phase. But perlite is a stable phase. Martensite is not. It is a metastable phase basically. And you just remember this diagram. This is a first curve. This blue curve, you can see this is the first blue curve. And this is a second blue curve in the TTT diagram. The first blue curve is showing your start temperature, transformation start temperature. This is the transformation start temperature. And this one is the transformation finish temperature or transformation end temperature. That means here you have unstable austenite. This unstable austenite will start transforming into some other phases at this temperature. This is a line, but this is actually not a line. These are one points. By joining these points, we have getting a line, right? Suppose I am keeping my steel at this temperature, for example, and I am allowing the steel to cool isothermally. That's why TTT diagram is also called IT diagram, IT, isothermal transformation diagram. So I am holding my steel at this temperature now from austenite. Initial my steel is at this temperature. Now I am holding the steel at this temperature. So what will happen? I am going down this temperature. Once I am going down this temperature, the austenite will not remain now. Austenite become unstable. So it will start transformation. How the transformation will happen? I will allow the steel to cool isothermally. So this is the time axis. Once it will touch the point here, the transformation will start. It will start transforming into perlite. But all the austenite will not transform into perlite at this point. It is a continuous process. I'm increasing the temperature, and when it will reach here, then all the austenite will transform into perlite. That means in between this line, we have a mixture of two phase, austenite and perlite. Similarly, suppose I am, my steel is here now, above the austenitizing temperature, and I'm quenching, right? Faster cooling to this temperature, 400 degrees centigrade, for example. And now I'm allowing my steel to cool isothermally. I will hold the steel at this temperature and I will allow the steel to cool isothermally. That means I have to move in this direction. So the moment it will reach at this point, it will austenite will start transforming into Bainite. Which kind of Bainite? You can see upper Bainite basically. And but all the transformation has not completed here. Now when you reach at this temperature, all the austenite will transform into Bainite. So this is the finished temperature, right? So in between this temperature, you have austenite plus Bainite. Similarly, suppose my steel is here now, and I'm quenching the steel. Quenching the steel means I am not doing very slow cooling. I am just cooling the steel continuously at a very fast rate from here. So what will happen? I am continuously cooling at a very fast rate. So what will happen? It will not touch this is the nose of the C curve, NOIZ, nose of the C curve. Like your nose. Your nose is like this. Suppose this is your face and this is your nose. This is your face and this is the nose. So this is the nose of the C curve here. So if you allow the steel to cool from this temperature continuously and at a very fast rate of cooling, so it will move like this. It will not touch the nose of the C curve. So there will be no transformation of austenite to perlite or to Bainite, but it will go down like this and it will touch this point. This is what? This is MS, martensitic start temperature, and this is martensitic finish temperature. That means your austenite will transform into martensite. Fine. And in between these two lines, MS and MF, this is called martensite finish, MF temperature. This is MS, martensite start. In between them, you have martensite plus austenite, unstable austenite, basically. And below this temperature, everything is 100% martensite. You understood now? I think you people have understood the TTT diagram. Yes or no? Just tell me quickly.
Yes, sir.
Okay, very good. And I told, do you people remember the problem with the alloy steel, the written austenite? Do you people remember that? Do you people remember what is the written austenite? I told you in the previous lecture. That's the main issue with a alloy steel or high carbon steels. What is an written austenite?
Sir, the austenite which doesn't transform to martensite and remain like that.
Okay,
That
very
is
good, very good, very good. You remember that. So what happens if written austenite will be there? What are the problems we'll face? Austenite is a soft phase or harder phase like martensite?
soft phase.
Obviously. So if you want only martensite, but in your martensitic matrix you are having some austenite, so what will happen?
Sir,
What will happen to the strength?
Strength will decrease.
Strength will decrease, obviously, because martensite austenite is a soft phase. The crack will initiate over there. That is a weaker portion, basically. Or if you keep the steel to a lot of time, what will happen? This austenite written austenite will further transform into some other phases. So due to phase transformation, the volume change will be there, right? So due to volume change, what will happen? The strain will create, or some residual stresses will be generated inside the material. That is the problem with written austenite. Anyways, so how written austenite forms basically? If this, can anybody guess in which condition the written austenite may form? The hint is just look at the MS temperature and MF temperature. It is basically like 230. This the start temperature is like 230 or 220, and temperature is suppose 150. What happens to this line? So the written austenite will be more. That is another hint. Another hint is I told, unless until while cooling, the steel, if not touch these curves, the transformation will not start. And if you will not touch this curve, the transformation will not finish. So that is another hint. Tell me quickly. I'll give you 5 seconds to think.
Sir, if we continuously cool that, instantly cool that, means the line will not touch that nose temperature fully
Then what
down.
will happen? Written austenite will be there. My question is, what is the condition to get written austenite?
Okay.
Rapid cooling.
Rapid cooling. Okay, rapid cooling. No. My question is, in which condition you might end up with written austenite?
When the gap between martensitic start and finish temperature is
More, you are saying. Do you think that is the answer? No. Okay, fine. Anyways, the thing is what? If this MS temperature and MF temperature will go down, just listen it carefully. This MS temperature and MF temperature will not happen at this temperature now. It will go down. Sometimes what happen, this MF temperature go below room temperature. You can imagine. Below 37 degrees centigrade for certain steels. Basically, for alloy steels and high carbon steels, this MS temperature, MF temperature go down below the original temperature. Right? So it will go down. Sometimes MF temperature will go down below the room temperature also. So what will happen? Now tell me, if the MS temperature, MF temperature will go down below the room temperature, what will happen? Or MS temperature will only go below the room temperature, what will happen?
when written austenite.
Written austenite will be there because the austenite cannot transform into, do not get time to transform into martensite. Right? It will simply remain as some austenite only. Right? So this happens basically in alloy steels and high carbon steels. This is one of the problem in alloy steel and high carbon steels. Because that is called effect of alloying elements. Some alloying elements lowered the MS and MF temperature. And in certain case, MF temperature go below the room temperature sometimes. Okay, fine. And this is the CCT diagram. CCT diagram means continuous cooling transformation diagram. Continuous cooling transformation diagram, that means we are doing continuously cooling. So what is the difference here? Can anybody figure it out? What is the change here? CCT diagram is up to this only. These darker blue lines. And these lines. It is written original TTT lines. But this is the real CCT lines. So what is the difference in between them?
Sir, no Bainite region is there.
Bainite region is there. Why there is no Bainite? Very good, Vijay. Why no Bainite region here? It is present in CCT.
So because we do that continuous cooling.
Due to continuous cooling. So if you do continuous cooling, which kind of microstructure will be obtained? It is clearly seeing which kind of microstructure is present.
That perlite and
Perlite and?
sir, martensite.
Yes, martensite. If you do continuous cooling of a steel, you will either end up with perlite or martensite. You will never end up with bainite, basically. Sometimes it may happen due to some reasons, but you cannot end up with bainite. I told you how to get bainite. Can you people tell me how to get bainite? What is the first stage you have to do? What is the first stage you have to go? Suppose I will give you a steel and I want a bainite. So what you will do? Start from, just tell me in a sequence. I will give you a steel and I want your steel should be have bainite now. What you will do?
Sir, we will cool after that.
Vijay, you will start cooling the steel.
Yes, sir.
From room temperature, you are cooling the steel and you will get bainite.
So for room temperature, we will heat.
Okay, Mansi, can you tell me the sequence? Just imagine now I am handing over you a steel and I want at the finally I can able to see bainite in that steel. So what you will do?
First, we have to heat the steel above eutector
Very good.
temperature.
First you have to heat the steel to what temperature?
To above eutector temperature.
To what temperature? But if your steel will be of hypoeutector steel, then
Above 7 to 7 degrees Celsius.
No. 727 is a eutectoid temperature. But I am asking if your steel is a hypoeutectoid steel. Then at above what temperature you have to heat? Just look at the diagram. I show you. That's why. Just look at the. Okay, where is iron carbonate? Just look at this diagram. This is the eutectoid temperature. And you are having this is the eutectoid composition. And you have a hypoeutectoid steel. So you have to heat the steel up to or above. This temperature. This temperature, because you can see the phases. Above this temperature, everything is austenite. But if you heat just above this temperature, you will be having ferrite plus austenite. You understood the point?
Yes, sir.
But if you have a eutectoid steel, then you have to heat above this temperature. That is eutectoid temperature or AE1. But for if you have a hypoeutectoid steel, you have to go above what? Which temperature is this? I told you many times. What is the name of this temperature?
Upper critical
Upper
temperature.
critical temperature. And what is the name? AE or A3. Very good. A3 or AE3. You understood now, everybody? So suppose by mistakenly you have heated the steel up to this temperature. What will happen? And you will do cooling. You do cooling. What will happen? Suppose by mistakenly you have heated the steel up to this and you are doing cooling. So what you will get?
Ferrite plus perlite.
Ferrite plus perlite. Ferrite plus perlite, right? But my okay, fine. So what happens actually? This austenite will undergo transformation to perlite, but this ferrite will not undergo any kind of transformation. Your purpose will be not fulfilled. You'll be end up with coarser ferrite. You understood?
Yes.
You end up with coarser ferrite and perlite. The perlite will be finer, but the coarser ferrite will be not. It will not undergo any kind of transformation. Basically, it will grow with time. So if you take in the steel over here and you are doing cooling, normal cooling, slow cooling, you will get finer structure somewhat, and you will get ferrite plus perlite. Okay. Anyways, my question, I am deviating from the main question. So tell me, Mansi, what you were saying? Yes. How will get a Bainite? The first you have to heat the steel above. If you have a hypoeutectoid steel, then you have to go above upper critical temperature. Very good. Next.
Then
What you will do?
Then we cool.
Then you have to cool
Then
or you
we
have to do quenching?
Cool it slowly.
Slowly? Oh God, I told you just few minutes before, you have to quench it up to Bainitic range temperature. Sudden, very fast rate of cooling you have to do. From here to, at this region, 550 degrees centigrade to, suppose 250 or above 300, in between this temperature range. You have to suddenly cool it to this temperature.
Yes.
Then you have to do holding. After cooling it to this temperature, you have to do holding. Then you have to do isothermal cooling. Right? If you want upper Bainite, suppose you are quenching it to 450. After reaching to 450, after quenching it to 450, you have to hold at 450. You have to give sufficient time to cool it to room temperature. So upon cooling, it will form Bainite, upper Bainite. Everybody understood now?
Yes, sir.
So that is the reason why in CCT diagram, what is missing? Bainite phase is missing. Because why? The name itself is saying. What is the name?
Continuous cooling.
Continuous cooling. We are doing continuously cooling. We are not doing any kind of holding at Bainitic region. Right? No holding is there. So what? Suppose your initial temperature is here. If you do, just look at this one. If you do a slow cooling means I will move like this. sorry, slow cooling means, yes, I will move like this and I will end up with coarse perlite. Suppose I am doing somewhat fast cooling, I will end up with fine perlite. If I will do very fast cooling, then I will end up with what? Continuous cooling. I'll end up with martensite. So continuous cooling always give you either perlite or martensite, but that perlite may be coarser or finer, that depend upon the rate of cooling. You understood? But if you have to get bainite, then you have to do fast quenching from the austenitizing temperature to the bainitic temperature region, and at the bainitic temperature region you have to do holding. You have to do isothermal cooling. Then you will get bainite. So that means, can you people conclude this topic? What is the significance of TTT diagram and CCT diagram? What benefit you will get by looking at TTT diagram? What kind of benefit you will get? What kind of benefit you will get? Because it tells us about the rate of cooling and the rate of cooling at the product form, right? Whether the coarse perlite will form or fine perlite will form, upper bainite, lower bainite, or martensite will form. All these things, information you are getting, and that depends upon the rate of cooling. You understood now? Or how to do phase transformation?
Sir,
Yes.
sir, Dinesh sir class.
Okay, fine. Now I'll end up. I'm ending the class here.